So I recently built this tool-post milling spindle that allows me to use live tooling and mill steel on the lathe. This opens so many possibilities, like milling keyways or drilling accurate hole patterns, to name a few. But my intention was always to also use it for grinding. So in this video, let's get grinding. External grinding to machine hardened steel and use it to build tooling for internal grinding and crank the spindle up to its full speed. But I'm getting way ahead, so let's go back in time, because the first part I want to grind is actually the spindle itself. When I was turning the spindle taper in the front for the collets, I had a hard time getting a good surface finish, but grinding should fix that, and on top it should also improve the runout, because right now it's about 2/100th of a millimeter. And for grinding I'm gonna use the side project from last time, which basically is another tool post mounted spindle.
Well, before grinding the taper, I obviously have to make the stone smaller with a dressing tool. But before that, I have to build a dressing tool holder. It seems like a universal law that whatever task you want to make, you're always required to make several smaller tasks prior to said task. Or is it only me? Anyway, I want to use this magnet base for mounting the dresser against the chuck and have some adjustability for the dresser angle. So the first part I made has a reamed hole in the center and a threaded cross hole, for which I, of course, used the spindle where I could even power tap. This part gets bolted to the magnet. The second part gets turned down to a precise fit with the hole. And then a reamed cross hole and another threaded one.
Well, this is loose. I can freely adjust it and lock it in position. Having the dresser mount like this I think is pretty useful, because if I have a part set up for grinding, I can still dress my wheel in between cuts and don't have to break down any other setup. But now let's see how well it actually works.
Grinding, and especially dressing, creates dust that's very harmful for the machine surfaces of a lathe. So before I start, everything needs to be covered. I even taped over the chuck and got dust collection set up. Once I touch the diamond, the dressing can begin. I'm taking about 30 microns per pass, so there are many passes. Looking sharp, and with my I don't care calipers, I check the diameter. This is ready to use. Before all that, I prepared a taper in a test piece that looked like this before grinding. I get the grinder into the bore until I see sparks and start making passes.
That is a really nice surface. It doesn't quite look like it, but trying to scratch with my fingernail along the surface, I don't feel any steps. Cool.
I played a bit more with different feed rates, which mattered a lot.
Oh, I'm very happy with that result.
And some Scotch-Brite smooths out the surface.
That was a really successful test piece. I hope I can replicate it for the actual spindle. The difference now, of course, is that the spindle will spin itself and the chuck stands still. I just need a way of powering it.
So before the whole grinding setup, I grabbed a scrap of plastic and cut a pulley from that, which screws to the spindle threads. After getting it from square to round, I cut the 3 V-grooves for the belt and then turned the hole for the threads. It's a pretty tight fit, which is good, and like this, it can go into the chuck with light pressure. With a longer belt, I could use the same motor as for the spindle.
Well, this setup won't win any awards, but it will for sure work.
Next, I needed to set up the compound angle to exactly 8 degrees, for which I again used an indicator. I need to measure 18.27 millimeters when moving the sled 130 millimeters, and that takes a few adjustments. But then, moving to 0 on the dial, and 0 to DRO, moving the sled until I read what I need, and the DRO shows 130 millimeters. Another quick dressing where I also dressed a step into the wheel, so only the front part will be in contact, starting the motor, and off we go again.
You can already see how it ground off more on this side than on this side, which means it's grinding away the runout.
From there it's just more passes. I went with 20 microns depth of cut and a very slow feed weight, which already took care of sparking out during the return stroke. You can also see what part of the grinding stone is in contact, which means that it's also correcting the taper angle a little bit.
Very cool result. Checking the runout with the Dell test indicator that shows 2 microns, it is basically no runout at all. I'd say that was worth it.
While already set up, I set the compound to 45 degrees and ground the chamfer smooth too. But what kind of surface roughness could I achieve? Well, Stefan has a surface roughness tester, so we could check. Nice, RA 0.4, which is pretty much the average of cylindrical grinding. Judging from my setup, I'm very happy with that. And here again the before and after.
All nice and well, but so far this has only been the necessary side project or Spindle build edition, and I don't want to be limited to just these tiny grinding stones. I want to use this size stone. Yeah, I decided on a 150mm diameter, 20mm thick stone, and for proper grinding speeds this will need to spin at around 3,000 to 4,000 RPM. And to do that accurately and especially safely, I need to come up with a proper flange that attaches to the spindle. And something like this usually starts as a 3D model in CAD. CAD is a very important tool for me that I use all the time, so it's very fitting that this video sponsors Onshape, a professional CAD and PDM system for engineers and their companies. And they currently offer the first 6 months for the professional version for free.
So the flange design started as 2 parts, the shaft with a taper matching the spindle, the diameter fitting the stone, and threads for the clamping nut. The second part is the actual flange disc, which will be a shrink fit on the shaft.
What you couldn't see is that designing these parts happened in my web browser, because that's where Onshape is built in. It runs in the cloud and doesn't require beefy hardware, so it runs basically anywhere on almost any device, even a phone. Additionally, the cloud offers several other great advantages. It, for example, records every single action you do, so you can revert back unlimited times to before you started making changes to your design. And here comes the best thing of all. It doesn't crash. You maybe remember my homemade oscillating belt sander project. I almost lost the entire 3D file and a month's worth of work because the software I used for this project wanted to update, so I saved my work to do so. But then while saving, it crashed, still updated when I restarted, and my file would no longer open and be corrupted, along with all the recovery files I had. That was a painful day of getting this file working again. Well, if I would have used Onshape for that project, the headache could have been avoided. So I can encourage every engineer or hobbyist to try out Onshape and get the professional version up to 6 months for free with my link in the description.
What's still missing in the design are balancing weights. A grinding stone is no precision machine tool, but will still spin really fast. So balancing needs to be accounted for, and that's integrated into the flange as well. But enough with the design. Let's print some drawings. And the first part I'm gonna make is the shaft, for which I have a nicely fitting but hard to machine material. This is the part that requires the most amount of accuracy and multiple setups, so I'm gonna turn it between centers. But to remove the bulk of the material with heavy cuts, I'm gonna start with the chuck. The last time this material chipped quite a few edges, but I got some more suited ones now, since this is a high strength stainless steel. Seem to do a good job. But this material is also super stringy, so the chips don't break, and this happens all the time. But after the heavy cuts, I could move to the big center drill, start the through bore from this side, and cut M8 threads. That's all from this side, so I could flip it, then part, and cut it to length. Next, the center drill from this side, and finishing the through bore. Then it's a bunch of stock removal, and the last job I could do in the chuck is turning the M24 threads. Now between centers, I could turn to final dimensions with a sharper and pointier tool, which takes finer cuts and creates less heat. But this still happens. Annoying, but doesn't affect the accuracy in the end. Some chamfers and flipping the part around to turn the taper. The beauty when turning between centers is that you can remove or flip the part and never lose accuracy. So after finishing these two surfaces, I could set the angle again to 8 degrees with the indicator and make a scratch mark where the taper should end. Well, and then it's just a lot of this.
Okay, the taper is almost done and I'm going to check the angle by looking at the contact pattern with the spindle. So marking it with dry erase marker, getting it out of the centers and rubbing it inside the spindle taper. I should see an even removal of paint. And it looks like it's a bit more in the front and the back isn't quite touching. This tells me right now the taper is too steep and I need to ever so slightly adjust my compound slide in the other direction.
Now the next pass should at first just remove material in the front, right there. Then another pass to recut the entire taper.
And the next test shows a little improvement, more towards the center, but still the end isn't touching. Another adjustment, third try. That's the same. Why? We're getting really close. 5 times the charm. Yeah, that's what I want to see. Nice.
I cut the taper to final length, chamfered it, and this first flange part is done.
The second part is the big flange section that will be a shrink fit onto the shaft and I'll turn it from a big piece of C45.
After removing the paint from the manufacturer, I turned the face and OD nice and shiny. Next, the big bore with the U-drill. This time it's not boring, but special with some slow-mo footage. There is a bit of smoke in the way, but it's so cool seeing the chips spiraling away from the tool. And then when it's a bit deeper and ejecting the chips. Sizing the hole then happened with the boring bar.
Looking for 31.97, right on the money.
A bit more material needed to go, which completes the turning for now, and I could continue with the milling spindle, but in its crosshole orientation and at center height. Like this, I could drill and ream the blind crosshole, then turning the chuck 180 degrees to repeat on the opposite side.
Okay, next I need to cut a big axial groove into the face, looking like this, a trepanning operation. But why trepanning when I can just use the milling spindle?
So spindle and lathe are spinning at the same time with power feed engaged. What could possibly go wrong?
Who would have seen that coming? But you know what? I got that in slow-mo.
Let's rewind, because it's quite obvious what went wrong. The lathe already spins as slow as possible, but the chip load was still too much, and eventually the spindle belt slipped right there. The lathe doesn't care about that and just took the end mill with it. So for the next try, I doubled the RPM to 2000 and used a 4-flute end mill, which will reduce the chip load quite a bit. That sounds much better. And the slow-mo confirms. Much healthier chip load and spiraling chips. The slow-mo also confirms that the spindle is nice and stiff, cause you can't see any chatter. Once at final depth, I disengaged the power feed and let it spin a bit more, which left a nice bottom surface. With the tool shifted a bit, I could remove more material from both OD and ID until I could fit a small boring bar to turn them to final size and get a good surface finish.
So far so good. There's one more operation necessary because this inner diameter actually needs a 2-degree taper that tapers inwards.
Nothing critical, so I just used the angle scale on the compound.
All pretty good so far, even with the broken bit. Now, these two pieces need to come together. I made them a shrink fit, so This needs to get hot, about 250 degrees. That went really well. Now that the parts are cooled down again and together, I can put them back between centers again and finish turn the flange surface true to the rest. And that's a complete grinding arbor shaft, which now provides a nice diameter and flange surface for the grinding stone. But to securely mount it, I need to make a couple more simple parts.
The first one is the clamping nut, so some boring, threading and hex milling with some more of this delicious slow-mo footage.
That's how it sounds, right?
While paring off, I interrupted to add the nut-typical chamfer and then cut it free. The second one is the clamping flange. That's just nice seeing the mirror-like finish of the facing cut. The rest is straightforward, but I had another approach for the chamfer by cutting it with a compound slide and then cut it off. And if you want to question this camera angle, you have every right to do so.
That's the stone mounted and it now fits the spindle, but to secure it, I need to make the drawbar.
As you might remember, when building the spindle, I made a through bore for exactly this reason. And the drawbar essentially is a long bolt, which I'm gonna turn from this stock. One end will of course have threads, and the last time I needed to make accurate small threads, I tried using a router, which worked. So now with a much stiffer spindle, it should be even better. Going at about 12,000 RPM, just 3 passes for a perfect fit. I like that. Everything else will happen between centers, so center drilling the end, then flipped around, I faced it to length, and center drilled it too. Now there's a lot of material to remove, and it's a pretty soothing type of work. You just have to remember to not get carried away or else...
Stupid me was enjoying the turning too much and I turned away material here where I shouldn't have. There needs to be a bigger diameter. Need to come up with some kind of fix for that.
But first, the finishing cuts with a sharper and pointier insert that doesn't generate as much tool pressure and heat and leaves a nicer surface. Just need to stop right about here.
Now having stopped the finishing cut where it's supposed to, this diameter is still a little bit bigger than here, so I can press a bushing on and then turn it to the right dimension.
So next, I turned said bushing from some bronze, got it hot to expand a bit and dropped it in place. Cooled down and back between centers, I had a second try. Having used bronze, it now even looks intentional. Simple way of turning a bug into a feature. Or at least pretending. Back in the chuck to mill the hex. Otherwise it wouldn't have been a very useful bolt. And even with the hiccup, this turned out great.
That's mounted and we can give it a spin. Slow for now, and next would be dressing at proper speed, but I'm not going to do that without a guard, so building one comes first. If you're wondering what this nut is for, it's for pushing the arbor back out of the spindle again, because this taper can wedge itself in place.
The design is similar to a bench grinder guard, but it will be mounted to the spindle housing, so I started with a mounting hub from aluminium and actually the chamfer, because later I won't have good access anymore. The big bore means some heavy cuts, first with the U-drill and then the boring bore. Super fun with aluminium, but the chips fly everywhere. So far so good. Next I needed a mandrel to flip the part around. Great! And I also made an expanding disc with the same diameter, which goes in first. Then tighten a countersink bolt, expands the disc and clamps the part from inside, giving me access to all outer surfaces. So I could finish all dimensions, add some decorative grooves and move to milling. I needed 2 counterbore and threaded holes for the clamping screws. All straightforward operations with the milling spindle, but threading I did again by hand, but guided. Then the 5 threaded holes in the face, and off the lathe it comes. Or not. Last step is cutting the slot, and that's when it turned into a nightmare. The part collapsed from internal material stress and clamped onto the blade. Insanely hard.
Eventually, I got it off again with minor damage, and this is how much it collapsed. It's almost 2/10 smaller now, and obviously no longer fits. So I tried machining in threads to spread it open again with the set screw, which wasn't enough, and I had to mill material away to make the whole part more flexible to be able to spread it open even more. About this much is necessary to be able to now slide it on. At least I no longer need the clamping screws, because there's so much tension in the parts that just unscrewing the set screw a bit is enough to clamp this properly. What a pain! Well, at least I learned a couple things and could try out this expanding mandrel part. But let's move on with the sheet metal parts now. I need this shape 3mm thick, and since it's mostly round, I can do part of it with the lathe.
I cut off a blank, prepared it into an octagon, and put it in the central 4-jaw chuck. Now let's see if this is a dumb idea. I'd say no. Next, I turned another mandrel, fitting the hole, and clamped the part with a bolt. Well, I didn't expect it to make music. But what am I doing? I have a milling spindle for the roughing. Much quicker. Now I was certain the insert would break from this, so I used an already chipped one and recorded it in slow-mo. First some nice chip formation. And here, the bang. Yeah, going straight into the edge like a parting cut worked much better.
That was fun. Unnecessary, but fun.
With my 3D print, I transferred all other features, drilled and cut them. Next, I needed to bend this strip of steel into a circle. There, I threw money at the problem and bought a small slip roll. Very fun to use. Almost. Jackpot. I cut off the overhang and set up for tacking. Then, without filler, I melted together the outer edge. Very happy with the result. Then I made threaded pins that get welded inside for mounting the lid later. Then some grinding to clean it up, primer and paint.
That turned out really nice, just like my long overdue haircut. It now goes onto the spindle housing, then the stone with the drawbar. And then I made a thick polycarbonate cover plate so we can see stuff, and one for dust collection while dressing. Now spinning it up for the first time. That's around 3000 RPM, about the grinding speed I want. Running pretty okay. Now for dressing, I have dust collection set up again, the lathe bed is covered, and we're also setting up the high-speed camera again with lots of light.
Dressing then is straightforward. Unfortunately, even at 6000 FPS, the footage wasn't really good this time, because the grinding wheel speed is a lot faster than the end mill speed, and you can't really see anything. We tried again with 30,000 FPS and pencil marks on the wheel, but didn't have enough light for a clear image anymore. Remember, this wasn't enough light. A lot to learn with high-speed footage.
Alright, the wheel is dressed all around and there are no more traces of the pencil mark. But before we can grind with this, there's one more important step necessary: balancing. And that's what this weird slot is for. It's for balancing weights that can slide and be clamped around here. So let's get them made.
They will make a ton of use of the milling spindle and begin from the same stock as the flange. I turned the end into a donut and made sure the OD and ID fit the ring slot in the flange.
From this ring-shaped end, I can now machine 6 balancing weights looking like this, and they all have a threaded hole in the face and a cross hole in the edge. And I'm going to start with the cross holes. I index my part to 0 and start with spot facing.
Then index to 60 degrees and go all around to do all operations with this tool. Next then is spot drilling, followed by drilling, and some deburring by hand.
And now ream to depth, such a steel ball can stick through but not fall through. Ball goes in. And I can't push it through. Good. And with the spindle like this again, I'm ready for the M6 holes in the face.
And that's more of the drilling and indexing stuff. The threads I cut by hand, but could use the spindle again as a tab follower.
With all the hole features done, I can now mill the parts into shape with a few cuts at specific angles.
I'm still working on my feeds and speeds, and that's not the sweet spot yet, but I'm getting there. The idea was a couple of roughing cuts, then turn the chuck to the right position for a light finishing cut.
And I've got 2 blanks cut out. I need to still find some better feeds and speeds, but that works.
More of the same, at least until I had more end mills, and lowering the depth of cut for the roughing passes to just 2.5 millimeters also helped a lot. While already set up like this, I also chamfered the edges. Yes, it's a woodworking rod a bit, but still, carbide cuts metal.
And that's the milling complete. Made quite a few chips.
Before cutting it off completely, I could chamfer the back edge and save some time later. But then the interrupted parting cut sounds terrifying.
From this, I can now break them free and then chamfer the remaining edges by hand. They turned out nice, but they also need to fit. Beautiful. Now the clamping works with this ball that drops in here, and this conical tipped set screw goes in from the top. By screwing further in, that will push the ball out and wedge the part in place. On top of the wedging, the shallow taper of the inner diameter will also prevent the part from coming out. Starting to look like a really serious grinding arbor with these balancing weights. Now for the actual balancing, you usually use a balancing shaft and a stand, which doesn't quite work in my case, but I have a similar approach. I made this shaft and bushing that both have the 60-degree center taper on them. They fit through the shaft and, like the lathe centers, can clamp onto the center bores of it. This should now run perfectly true, since it's referencing off of the same center bores the whole part was machined on. And like this, I can put it onto a balancing stand. Except I don't have one, but my lathe bed is the most level surface in the shop, and putting it on that with 2 gauge blocks on edge is essentially the same. With no weights installed, I give it a light spin and let the heavy points settle at the bottom. Let's confirm from the other side. Okay, heavy point is now down, so I add a weight on the opposite side on top. The other 2 weights equally spaced on the heavy side. Now repeating the test, looking for another heavy spot. Looks like I found one, so shifting the weights a bit. Pretty happy with what I'm seeing here, so I tighten down the weights fully and the balancing is done. And although I didn't use the taper to balance it, since it was machined between centers and now balanced between centers, it should still be balanced when I install it back in the spindle. Ready for grinding. But what should we grind? Ideally something hardened and precise. So to start off with, I was thinking about more accessories for the spindle.
For one, 3 different sized internal grinding spindles, an adapter for a chuck, and why not also a slitting saw arbor?
Yeah, let's make all of that.
All 5 are simple parts and start from this long piece of 4140, starting with the small internal arbor, and the first task is drilling a center hole, and the threads for the clamping screw. Then a bunch of stock removal and cutting it off. Flipped around, I cut it to length, drilled a center hole as well, and then the M8 threads for the drawbar. Then, between centers, I could finish turn the end to fit the grinding stone. With the compound sleds set and dialed to 8 degrees again, I could prepare the spindle taper. Pretty quick to do, but leaving some material for grinding. Like this, I then also prepared all the other blanks.
Okay, I got 5 slightly oversized blanks. I left about 1/10 of a millimeter for grinding. Next, I need to harden them.
So I put them all in an oven to bake at 860 degrees and hold that for half an hour. Glowing red hot, I got one out and quenched it in a bucket of water. And again.
Alright, they are hardened and I can confirm because the sound and feel of this file, it can't really take a bite. But I am quite amazed by the amount of oxides that flaked off during quenching. Quite a lot. But that was the first time I hardened any steel, so what do I know? Let me know what I can improve.
I put them back in the oven for tempering at 150 degrees for about 2 hours to get them a bit less brittle again. The next day I got them out again, cleaned the centers with Scotch-Brite and installed the first piece for grinding the taper. That means setting up the taper angle again, installing the spindle and doing another dressing pass with the step again to get less grinding pressure. Then moving towards the part until it touches, 20 microns depth of cut, and let the sparks fly. It's working, and it's amazingly quiet.
Ooh, that is nice. Now to check the fit with the spindle, I unfortunately have to disassemble all of the grinding stone. Again, dry erase marker on the taper. Let's look at the touch marks. Almost perfect, I would say. Just not touching at the end again. Yeah.
So a slight adjustment, redressing the wheel again since I had it disassembled, and another couple passes.
That looks very good to me. Very even in the middle, a little bit left on both ends. I think that's fine. So with the angle now set, I can speed through all the other tapers pretty quickly.
So I grinded this one to final size, swapped to the next one and ground it down. Here a full pass. Quite mesmerizing to watch how the sparks leave behind a beautiful surface finish.
This one you can see also bent quite a bit from the hardening.
But that's why I left everything oversized and could now grind it straight again. Rinse and repeat.
Alright, tapers are done. Now I can set up the grinder straight again to clean up all remaining surfaces. That should be fun.
There were also no dimensions I had to nail, just grinding until shiny and experimenting with different feeds and speeds. Wow, in the end all this produced quite a bit of grinding dust and a funny looking buildup on the guard. The spindle also looks quite covered. Let's take a look inside and see if my labyrinth seal is any good.
Fully clean. Good.
And there are all my results.
Very, very happy with these results. But what do the numbers say?
Bringing back the surface roughness tester and we get RA 0.2 and RZ 1.5. Both excellent results and at the better end of average cylindrical grinding. How does this compare to a store-bought and ground Morse taper adapter?
Yes, mine's better. Let's also see the runout when one is installed. We are looking at roughly 110mm stick out and just under 2/100th of a millimeter runout. Similar numbers for the rest, and since they're tooling, let's put one to the test.
My test specimen is this Morse Taper 6-4 adapter sleeve that came with my lathe with a questionable surface finish and a terrible 2/100ths runout. A job for the medium-sized arbor and stone, and there's a plastic washer between the stone and metal so it doesn't crack. It needs to spin at about 20,000 RPM, so I let the spindle warm up first at lower RPM for about 10 minutes while increasing the RPM a few times.
For dressing this one, I made another 3D printed dust collection piece that fully encloses the action. Only downside, you can't really see a lot anymore.
But I managed to squeeze the camera in somewhere. Okay, now get the stone in the bore and bring it up to speed. Then it's similar to before, looking for the sparks, set some depth of cut, and go. The uneven sparks tell me the runout gets removed.
Alright, done for now. The bearings are pretty warm, that's okay. I keep the motor running for cooling air because it and the aluminum plate, or the whole drive, that got pretty hot. The surface finish is a lot better. Runout is essentially 0 and this is the fine indicator. And checking the fit with a Morse Taper 4 sleeve. Pretty even contact pattern. So I'd call this and the internal grinding spindle a success. But this medium-sized stone was only spinning at 20,000 RPM. The small one needs 30,000 and the spindle should be able to do that. I left you with a pretty bad cliffhanger when building it. But now, let's do it for real.
So, switching to the highest belt setting, go through the spindle warm-up again and crank it up.
That's 30,000. But even though, it's still relatively quiet.
Most of the stone gets removed because it's intended to be only 30mm in diameter, which then looks like this. I chucked up a test piece with a hole and started grinding. But essentially, it's the same as before.
It totally works, but at those speeds, the spindle gets really hot and I had to actually cool it down right after the 10 minutes of dressing and after grinding this little test piece. The problem isn't even the bearings, they can handle that speed and got fairly warm, but the belts, due to their friction, got really hot and even deformed my 3D printed cover. This used to align nicely here. They are perfectly suited for the milling speeds, like up to 10,000 RPM, but for the really high internal grinding speeds, they are kind of the wrong choice. And a flat belt or direct drive and a different motor type configuration would be better suited. But you could see they can handle it for a certain amount of time, and since my main application is still milling, I'm totally happy with the performance.
There's another part to test, and that's the slitting saw. And well, it cuts a slit.
Not the most useful part for this tool-post spindle, but worth trying. The actual project was about the external and internal grinding arbors, which I'm very happy with, and I have more ideas to put them to use, so don't forget to come back.